Hello, everybody. Last time we discussed BigM method with equality constraints. So we quickly recall the matrix form of BigM method. So the original problem we considered is maximizing objective function and such that with a constraint. So you may have two sets of constraints. One is less than or equal, and another one is equality constraints. And of course, we assume every variables are greater than or equal to 0, which is signed constraints. Now we talk about, so whenever we have this less than or equality, then we can add select variable and that becomes a pivot. But if you have equality, there's no room to add select variables. But in RPM method, we say, okay, we can still add select variables or artificial variables and then punish it. So what it means is we can just copy, to formulate that, we can just copy this, the whole thing, and add artificial variables. So I just copy this down, the whole thing, but for the augmented matrix, when we have only square less than or equal, then you can put equal sign, but we will add select variable. I need more space. And if for equality, original equality constraint, there's supposed to be no room to add another artificial variable. Otherwise, the problem is changed. So if we add artificial variable, which is called xe, which is xe is a vector, column vector, which has the same length as be. So the number of equality constraints. Then if you added xe, then we are going to subtract mxe from the objective function to penalize that modification. And the theory says, so here xe is a column vector, so what we need is we change xe into sum of those xe's. So here 1txe means it is a number, so 1, it's a vector of appropriate dimension, the same number as xe, the same dimension as xe. All right, so that means this is xe1 all the way xem. So it's a number, and multiplied by m, this is how much you want to penalize. So the theory says whenever you have this modified zm, then you can make m as big as you want, and finally you can have the desired z star of original problem. So first of all, easy observation is zm star for the modified problem, because m is a parameter which you can give, you can determine, but as m increase, we can see that as m increase, the objective function is decreased, so the optimal solution is also decreased. And also, the next thing is that it is decreasing to z star, which is original optimal value, as m goes to infinity. All right, next we look at our LP problem with surplus. Now, our new problem is to consider following LP problem. So we write LP here. We can actually, yes, we can just, so we have z equals ctx, objective function, and we have constraint so those are all the same, less than or equal sign, but there is surplus constraint, which is the different point, different constraints, which was not included in the previous discussion. Now, if we look at BigM method, so we also want to assume, we always assume right hand side of constraint is or greater than or equal to 0. If not, you can just multiply -1 to get both sides, to get to make sure right hand side is greater than or equal to 0. For example, if I have constraint like x1 plus 2x2 less than or equal to -1, then what you can do is multiply by -1. Then that is the same thing as -x1, -2x2 greater than or equal to 1. So make sure this is positive number. So we have this problem. Then for this, naturally we can add artificial variable, which is we call slack variable. And another one here, we can add equality artificial variable and then punish it in objective function. What about here? If we have excess variable here, a surplus variable here, surplus variable, then make it equal sign. We will see. So we will copy. So we write LPM, but first of all, yes, here. So I just copy that, but what I need is I'm going to add some artificial variables, but if there, and sometimes we need to punish the objective function. So for the first one, it's very natural. We add one variable, then we can change this to equality. There's no punishment is needed. For second one, it's already equality, but because there's no pivot rows, appropriate pivot rows, what we want is we can add xe, artificial variable, then punish it. The last one we have, because this is greater than or equal, then if you subtract some positive number, we call that, let's say, x bar L, then we can make it as equality. Then we can make it as equality. However, if we do the simplex method, we cannot find pivot position from the last set of constraints because negative x bar L equals BL means x bar L as a pivot position becomes negative BL, which is negative number, not feasible. Then again, we do the same trick. We add another set of artificial variable. We call that XL. But for this, we need to again penalize the objective function corresponding to XL. All right, then what we need? If we, so the theorem again, the same theorem, ZM star, so the optimal value of RPM problem is decreasing as m goes to infinity. And if you increase m, and if increase m until infinity or big number, then at some day it will converge to z star, which is originally wanted. So originally wanted here, this problem, the z star. All right, let's look at an example to understand the whole mechanism. So the example is again, we're looking at two for simplicity. We just think a minimization problem, which is concerned with two decision variables, but their constraints are given three sets of constraints. So one is less than or equal to 2.7. Another constraint is equality constraint. And another constraint is, this is the constraint still less than or equal to -6. But here, when we start for BigM method, we first need to prepare everything we needed. So first thing we want to do is we want to standardize the problem. One, we want to make minimum problem to maximum problem. And two, we want, if we look at this right-hand side, positive, positive, negative. So this guy is negative, then you want to change negative number to a positive number by multiplying both sides of this inequality to multiply by -1, which flips the sign, but at the same time, -6 becomes +6. So first we do maximization problem, which is z hat. So instead of minimizing z, we want to maximize z hat, which is defined as opposite number of z. So that's the same thing. And for this inequality, if we multiply the last one here, xi greater than or equal to 0. Yeah, xi greater than or equal to 0. If we actually we need to flip each term of this third constraint, flip the sign. So negative becomes positive, negative becomes positive. So here positive. But don't forget to, when you multiply by -1, the inequality flips. So at the end, we have a standardized problem, maximizing problem, and right hand side is all positive numbers. So the right hand side. Now we do the BigM method. So to do that, we can just copy that the whole thing around. Maybe I should take another page. So the BigM method, I just copied the paste, there's nothing changed. But what I need is first I will leave a space for those artificial variables. And for this less than or equal sign, we can add xs, the select variable x3, and then we're allowed to change less than or equality to equality. For the equal sign, we can add x4 here, but this one should be punished. So this is mx4. Here for the greater than or equal sign, we have excess variable or select variable again, x5 here. If you take this out, then of course we can put this as equality. And if we directly use this one, if we directly use the third constraint here, then when I have x5 as pivot position, then if x5 is pivot for constraint 3, then x5, that means x5 is negative 6, infeasible. So this is why we need to add another variable. So here, right after this, which is x6, and then we have to penalize x6. So the matrix form is essentially can be converted into this form. And for this, we are going to do the tablet. So let's say this is pre-initialized initial tablet. So when we do that, we can write this as the first row. So the first row becomes negative z plus 0.4x1 plus 0.5x2 and 0x3 plus mx4 0x5 and then plus mx6. That's so we need for the tableau we want to put the whole thing on the right hand side to the left hand side and leave 0 to this to the other side, and then we can just copy the whole thing here. now basically we pull out all the coefficient. Make it a tableau. This is almost the end. So the tableau is going to be so we write the objective function -1, 0.4, 0.5, and for x3 it is 0, and then so 0.4, 0.5, 0, m, 0, m, and this place is 0. 0.3, 0.1, 1, 0, 0, 0, 2.7, 0.5, 0.5, 0, 1, 0, 0, 6, 0.6, 0.4, 0, -1. No, I miss another 0 here. -1, 1, and 6. All right, this is not yet an initial tableau because we need to, our pivot positions are these ones we add in. So if these are pivot position, you need to make sure using these pivot position to clear up every non-zeros in its column except itself. So for example, here we have this guy. We have this m is non-zero, so which is should be cleared up by pivoting. And to do that, we need for here to clear this m. What you need is R0. R0 stands, so this is R0, this is R1, row 1, row 2, row 3. So row 0 minus m of row 2, which replaces row 0. Now the same thing happens to here. So if we look at the last pivot, then we have m here to be cleared. So that means here we do another pivoting. So when you pivotize the last pivot column, then we have the following final tableau. All right, now the tableau, after we cleaned this up, so there's supposed to be, so originally there was m and there was m, but now it was 0, 0. But instead we have this is becomes -12m, and these two are also changed. So we have initial tableau from here, and then we can do all those pivoting and updating the tableau, and at the end we come up here. Now let's look at this BigM method and the final tableau. So for example, here we can first think of m is very big. So for example, -1.1, m is 100, and plus 0.4, this is smallest, then we can do the entering variable here. And with the minimum ratio test, we update. So all the way to the end, when we stop We stop here. And this tableau after certain amount of update. And what is the solution? So first we need to know how to read the final tableau. So first of all, this guy is going to be the optimal value for z hat. So this is equals our ZM. This guy is ZM star and the optimal value is, it takes optimum value when, so if we scroll the first one, so this is pivot position for the first row, so then 7.5, so x1 7.5, and if we look at the second row, this is pivot position, so x3 equal, oh no, this is not pivot position because there are a lot of non-zeros, so this is pivot position. x5 is 0.3, and from the third row, this is pivot position and 4.5. And otherwise, other variables are zeros. Well, another interesting question we can see that what's the minimum m so that such that zm star equals z star. So this question, so we know that if m is big enough, for example, m equals 100, then the tableau gives the number what we needed, so it will be the same as z star. But the what is the smallest m? Of course, m you can take 1 billion, but this gives a heavier computation for the computer. So what is the smallest m? Then what we need to know is we observe the last tableau and see this one. So the last tableau means the last tableau stalls because this everything is positive number. But why this is positive number? Because m is big enough. How big? As long as m minus 1.1 greater than or equal to 0. So it's so that means m. This is for answer m greater than or equals 1.1. In other words, the minimum m minimum m equals 1.1. So if you take 1.1, the tableau goes to the optimal value wanted. We also want to know what if m is smaller than 1.1. Then we can look at a project. An interesting question we can ask is, what is the m is changing? When m changing, it changes zm star. And we know that when m goes to 1.1 or even bigger, then it gives the final value, which is negative 5.25. So if we look at this mapping as a function, then what does it look like? So basically we can ask, find z star m as a function of m. For this question, so we can look at the first row here. So if for first row, if m takes a range of numbers, then it will stop. So when this supposed to be stopped, then the question is, so we don't need to go to 1, 2, 3. So the condition to let the tableau stop at the beginning is everything is non-negative. So the smallest number, because m is greater than or equal to 0, the smallest number is here. So tab 0 stops if negative 1.1 m plus 0.4 greater than or equal to 0. And that time we have zm star, which is taken from negative 12m, if m is less than or equal to 4 over 1. Now we look at tab 1. Tab 1 is here. So next, so suppose m is greater than this number, or not 1.1, this is 11. So if we look at this number, this tableau, this stops. The smallest number here is this one. So this guy is positive. At this moment, this is the optimal value, and zm star equals negative 0.2 m minus 3.6. And next, tab 2, similarly, it stops if this guy, not this one. Yes, this one greater than or equal to 0. So if, or here, so if this, and I need more spaces. So negative 5.3 m plus 611 greater than or equal to 0, and ZM star equals negative 0.5 m minus 4.7. Now tab 3 already is given here. This is tab 3. Tab 3 stops. Alright, we are going to stop here.